Coincidences aren't always coincidences. Imagine for a moment a game of pool. The balls are placed in a triangle, and the pool player lines up the shot. He shoots. The balls scatter, but then, against all probability, they all start falling into the same hole, at the same corner of the table. What would you think if you saw it in that moment? Are you likely to chalk it up to a probabilistic fluke, or perhaps some skill on the part of the player? Or are you more likely to start checking under the table that no one's done something to lower one of the legs? Some things in our universe are so improbable, they really shouldn't ever happen. Think now about our solar system and imagine a large mass came screeching into it, large enough and at just the right angle for its gravity to wobble one of our planets out of its orbit and to scatter that hapless planet into interstellar space, like the balls on a pool table, but a whole lot bigger. What are the odds that that mass would knock out not just one planet, but two? And that those two planets would head off in the same direction at the same speed, enough that once out in interstellar space, they would start orbiting each other. The odds are astronomical, but I suppose it's technically possible. And so it's not a complete surprise that the James Webb Space Telescope has just found an example of exactly this going on in the Orion Nebula. In the space between stars, two planets are orbiting each other. Each of them has a mass similar to that of the planet Jupiter, so scientists called them Jupiter mass binary objects, or jumbos for short. But the Webb didn't find just one example of jumbos. It found 40, representing almost 1/10 of all the wandering planets that JWST saw in Orion. That's not just unlikely, that's downright suspicious. So much so that it's time to start checking the legs of the universe to see what's going on. Join with me today as we investigate jumbos and try to find clues to explain just what might have caused such objects to occur so frequently in Orion. One thing scientists all agree on: our models for the formation of stars and planets are certainly wrong, but in what way is still to be discovered. Jumbos were first seen by the James Webb Space Telescope in October 2023, when it turned its awesome high-resolution instruments on the Orion Nebula. It's possible jumbos exist in other places too, but they have remained undetected for now, probably as their relatively small size makes them quite difficult to spot unless you're using techniques like gravitational microlensing, which is in and of itself a highly randomized way of finding new planets. Gravitational microlensing, seeing the momentary increase in a star's brightness due to the relativistic effects of an object passing in front of it bending more of its light towards you, is an event so unlikely that Einstein thought we'd never actually catch it happening in nature, even though he theorized it was occurring. While technology has improved to the level that we can actually take advantage of gravitational microlensing as a way of spotting new planets, mostly by developing some wide-angle telescopes, you still need a jumbo to pass in front of a star before you can see it. It's not surprising that relying on such randomness has left a lot of planets slipping under the radar. We needed a powerful telescope like the JWST to give jumbos a proper look. But when we did discover them, they were a total surprise, one that no one in the scientific community had seen coming. The ones seen by the Webb are relatively young, only 1 million years old, compared to our own Earth's 4.5 billion years. But the strangest thing about them is how they orbit. Instead of orbiting happily around a neighboring star or drifting through the vastness of space like most rogue planets we have discovered before, jumbos orbit each other. They are binaries, gently caught up in the gravity of the other at a distance of around 200 AAUs or 200 times the distance between the Earth and the Sun. Frankly, this is baffling. Binaries aren't completely unheard of in our galaxy. In fact, they're relatively common. About 1/3 of all the stars in the Milky Way are binary or higher, meaning it's quite natural for orbiting bodies to take this configuration. However, the smaller you get for the size of your star, the less this tends to happen. 75% of massive stars are binaries. For smaller stars, this number drops to 25%, and for objects smaller than a brown dwarf, which aren't big enough to ignite into fully fledged stars at all and are only around 15 to 75 times the size of Jupiter, it really shouldn't happen ever. Jumbos ought to be impossible. There should be no reason their frequency should suddenly uptick to roughly 1 in 10. And yet, that's what the JWST saw. When it surveyed the space within the Orion Nebula, astronomers were excited to spot 540 different planetary mass objects much smaller than brown dwarfs. And of these, 9% were orbiting each other in these binary pairs. 2 were even circling in a triplet, which is really rubbing probability's nose in it. 9% is an astonishing number at this scale of mass. As soon as scientists realized jumbos were this common, they immediately recognized that our models for the formation of planets couldn't be correct, as there are only 2 explanations for where jumbos could come from. The early days of a planetary system are always chaotic. You've likely seen artistic depictions of a molten Earth in its early infancy, with comets and space debris raining down on it. This space debris was far more common in the solar system's infancy, where dust coalesced into rocks, then into asteroids, and eventually into planets with enough gravity to pull everything in around them, causing cataclysmic collisions along the way. Sometimes that gravitational pull was such that it didn't smash 2 objects directly into each other, but instead pulled them out of orbit and left them careening into deep space. This can even happen to very large planets, if the circumstances are right. For example, it is actually theorized by some researchers that our own solar system used to have one additional gas giant which was bullied out of our solar system by Jupiter or possibly Saturn, although the smart money is on Jupiter. Jupiter's gravity was enough to tug on this other gas giant until it was sent spiraling out into interstellar space. We've asked on this channel before whether there might be a planet 9. We didn't consider that Jupiter actually might have given it the boot long ago. Regardless, the idea of a planet being sent out into interstellar space, even a large planet the size of Jupiter, is not that extraordinary. Indeed, it's believed that wandering planets of all sizes are fairly common. There could be billions to trillions of rogue exoplanets wandering around in the void of space between planetary systems in our galaxy, which, if true, means there are more flying around out there than there likely are orbiting stars. Something else must be going on. But the alternative explanation for the formation of planets doesn't work either. This second theory states that in the aftermath of a large supernova explosion or through the force of solar winds, hot matter is sent flying in all different directions away from the center of a nebula. Cosmic dust pushed outwards in this way is also pushed together, helping it begin to coalesce due to gravity and form new stars. But if stars can arise in this way, why not planets? After all, to push enough dust together to make a star, you at some point will have an object the size of a planet, right? But no, not on its own. While this happens in the nurturing planetary disk of a newly formed star, it turns out that without that extra gravity, an aspect of gas physics stops this theory from working in interstellar space, or at least for objects of that size. It turns out that something called the opacity limit puts a lower threshold on the size of objects that can be formed this way without a star. They either come together to form at smallest a brown dwarf, or they resist coming together at all. In other words, interstellar dust and gas go big, or they go home. It works like this. All objects have gravitational potential energy. When gas coalesces together due to gravity, it loses that gravitational potential energy. That energy has to go somewhere, obviously, so in nature, it tries to radiate away as heat. This is all very well and good when the gas is spread out, but once more and more gas starts gathering in, as you might see when gravity is pulling in material for a planet, then everything gets cloudier and cloudier or more and more opaque. This actually makes it harder and harder for this heat to radiate away, so instead things stay hot and energetic. This pushes back on any more material coming together. A delicate balancing act is thus reached, where hot gas that just can't quickly cool down pushes back too hard against gravity for any planet to form. Stars get around this problem by having a little extra oomph in their formation. There is a reason stars tend to form in nebulas. This vestigial extra push is enough to overcome the hot gas dislike of pulling together. But once you push past that barrier, you already have too much oomph to form just a planet. Now it's a brown dwarf or something bigger or nothing, which is why scientists are searching around for an additional ingredient, something that might explain how a jumbo might still form in interstellar space. To me, this explanation seems like the neater one. If somehow you could overcome the opacity limit, you'd end up with planets naturally arising out of interstellar matter. If two Jupiter masses formed close enough to each other, they would drift slowly together and could quite naturally take up orbits around each other, with no star required. Nothing about this relies on crazy probabilities as the first pool table leg planet theory asks you to believe in. There could even be planets smaller than Jupiter masses out there, doing the same thing. Two Earth objects are even smaller, just too tiny to be caught in even the JWST's camera. But perhaps an old theory can provide an answer. In 2001, long before we had any idea jumbos might exist, a researcher called Alan P. Boss published a paper in the Astrophysics Journal about the way objects slightly smaller than the mass of Jupiter could form from interstellar matter, provided that magnetic fields are active in the formation process. In effect, jettisoning out the newly formed planet mass from the growing cloud that was about to become a brown dwarf, leaving the rest of the cloud to continue on its way towards collapse and stardom while preserving the smaller planet intact. The paper admits that it's conjecture and says that more work needs to be done to verify the idea, but I find it intriguing that the sizes in this theory match the reality of jumbos long before we saw them. Maybe jumbos weren't entirely a surprise after all. Is magnetism the answer to jumbos? It's too early to say. All we know for sure is that we know less than we previously thought. Jumbo's existence calls into question our models on the formation of stars and planets and shows us more research is desperately needed. But then, that's half the fun of science. A theory is all well and good to have, but when you find something that throws off your theory, it's not a bad thing. It's an exciting discovery and an opportunity to get an even better understanding of the reality we live in.